Hello everyone, our project is Let's Catch Pokemon. We all know Pokemon Go is a mobile AR game where players can catch virtual creatures Pokemon, use GPS and camera on their phone. And in this project, we predict where Pokemon may appear and what kind of Pokemon will appear. And then we find some similar Pokemon based on historical data in Pokemon Go. We divided it into 4 parts, and here's our content. And I'll introduce the first part, dataset description and realization. And this is a dataset from Kaggle, and its name is Predict Them All. It contains roughly 293,000 Pokemon sightings. From the picture, we can see that it contains ID, latitude, longitude, appear time of day, terrain type, and many other features. So let's take a quick look of the dataset and what we can get from the original dataset. The first picture is the distribution of Pokemon in the world. And we can see that most data come from America and Europe, and the color of the scatter points in this map represents different kinds of Pokemon. It seems that most of the Pokemon are distributed all around the world. We can catch most kinds of Pokemon even in one city. And then let's take a look of how different kinds of Pokemon distributed among cities. This is the distribution of Pikachu in cities. We can see from the y-axis that it is a really rare Pokemon. And we can also find most of Pikachu can be found in New York. And this is the distribution of Omanite, and it's a less common Pokemon than Pikachu. And a lot of them can be found in Los Angeles. This is the distribution of Pidgeotto in cities, and we can see that this is a common Pokemon. And it also, most of those can be found in New York. So from the above, we can see that different Pokemon have different distribution among cities. Some Pokemon may have higher appearance probability in some certain cities. Let's take a look of how Pokemon behaved in different time of the day. We can see from this picture that in New York, most Pokemon appeared at night, and in Prague, most Pokemon appeared at daytime. This may be because the most commonly appeared Pokemon in New York may be more activated at night, and the scene is different for Prague. So to increase the chance of catch a specific Pokemon, we should know how Pokemon ID related to cities, time of day, and maybe many other features. So in the next part, we'll introduce some models we train to predict it more precisely.
After data preprocessing, we like to use the dataset to do something interesting. First, we try to predict possible location for Pokemons. Since some features like weather and close to water are not numeric, we encode them. Also, in order to improve learning results, we scale some features to suitable range. The training model we choose is gradient boosting tree regression. The training process and rules are as followed. Here, the score is coefficient of determination, and we use it to evaluate our training performance. The score we got on latitude is 0.94, and the score on longitude is 0.95. We then use base map to visualize the test results. The red area are test label, and the blue area are results we predict. Since the latitudes and longitudes in test data are close, it seems that the red area are more concentrated, but actually the results we predict and the test label have same size. Then we try to predict possible Pokemons according to geographical condition. We first use all columns except Pokemon ID as features. No matter we choose what kind of model, we couldn't get good training result. We then did correlation analysis to pick out more efficient features. We found out that these features like latitude, longitude, continent have higher correlation coefficient with Pokemon ID. Hence, we picked them as features. Also, we used one-hot encoding to encode some features. Then we used the k-nearest neighbor classifier to train the data. The score we got is 0.84. Here the score is used to evaluate the accuracy of KNN learning. We also use Seaborn to visualize the result we got. The blue columns are true data and the orange columns are the results we predict. There are some difference between the true data and the predict data, but the result is acceptable.
One of our functions is to find the most similar Pokemon based on our features. The pre-processing of data is similar as before. Here we choose the Manhattan distance as our measurement for similarity. The similarity is shown in heat map here. The lighter color means the shorter distance. For each row, we find 5 nearest Pokemon, which means the 5 most similar ones. Because we get the ID in this matrix, we convert the ID into name by another file. Then for the difficulties and problems, there are 2 points. Firstly, the data needs to be processed. There are many abnormal values. For example, some strings appear in numeric columns, just like the distance to stop. Then, some features are redundant, just like urban and rural. This may bring about noise to our features. Finally, some features are categorical data, just like we have different cities and weathers. To solve these problems, firstly, we check abnormal values and delete some samples. Because most of our samples are right, this will not influence our data. Then, for the redundant features, we use correlation analysis to delete some features. The measurement here is the Pearson correlation coefficient. We delete the features like time and urban. We prove this is really helpful for our accuracy at last. Finally, for the categorical data, we try to convert them to an integer directly. But this is not a good idea. Some categories have many different types, just like we have over 40 cities. The ordinal relationship doesn't exist between different types, so simple integer converting may bring some noise. Thus, we choose one-hot encoding here for the weather, city, and etc. One-hot encoding extends our feature space and helps us get a better result at last. Then for the model selection, we choose gradient boosting tree algorithm to regress the location. This model is great for fitting the data, but it is easy to be overfitting, so we spend a lot of time on parameter tuning to avoid overfitting. Finally, we achieved over 95% accuracy on test set, which contains over 80,000 samples. We also chose k-nearest neighbor classifier as our classification model. This is a simple and non-parameter model, but because it is really effective when data is really large and noisy, it is fit for our data. We get over 85% accuracy finally.
行了，说完了，必须要嘚瑟。